Starting off from where we left off in the previous class, the idea about what is an electric potential. There's a charge, tiny test charge Q1, which is at a certain position. It experiences a force according to Coulomb's law. You do some work pushing this closer, it gains electric potential because it comes to an area of higher potential, so there is larger force. And when you allow that force to move freely, now it's going to obviously shoot back because there is no other force to prevent it from doing so. And when it goes from this point to this point, then it is going to be able to do some work for you. So the question that has been raised now is about what is known as the electric field. Electric field is actually not strictly speaking part of our syllabus, but we can go into it. I think we briefly dealt with it in class 9, but I'll just talk about it. So what is an electric field is that if you have a positive charge or a negative charge for that matter, then the electric field is defined as lines of force that emanate from this object, much like gravitational field lines. There are field lines that will emanate from this object, okay, radially outward. All right, and the field lines have some properties, like for example, if it's a positive charge, then the field lines point outward. Okay, why is it like that? That is because of a convention. We have chosen the convention of a tiny positive test charge. So if you place a tiny positive test charge in the vicinity of this, the test charge is going to be pushed outward, therefore the field lines are also pointing outwards. So that is one property of the field lines. The other property of the field lines is the density of the field lines at any given point gives you the strength of the electric field. Okay, so obviously if you come closer and closer, there are going to be more field lines. As you go further and further, there are going to be lesser field lines. So the density of the field lines determine what is the strength of the electric field at that point. And of course, the field lines, I am showing this in 2 dimensions. In 3 dimensions, the field lines are going to be somewhat like a pin cushion or a porcupine. There are lots of field lines that are going to be coming out in all directions from that positive charge. And naturally, if you have a negatively charged object, then the field lines are going to be reversed. I'm just showing it with a different color. It's not necessarily so that they are shown in green color or blue color. So these will be the field lines, and naturally now the opposite will apply. The test charge is always positive. So if you have a test charge of Q1, a positive test charge of Q1, then naturally this is going to be attracted towards it. So therefore the field lines for negatively charged object point inwards. Okay, and everything else is exactly the same. The strength depends upon the density of the field lines. It's 3-dimensional. It's all over the place. So now what was your question about the field itself, Ishan?
Yeah, so you do, yeah, it's so like if I'm comparing it to gravitational potential energy.
Yeah.
So in that also, the like when you gain an potential energy, work done is negative by gravity, right? By gravity, work is negative, right?
Gravity is pulling it downwards, and the displacement is also in the same direction. Theta is 0. So therefore the work done by gravity on the charge is going to be positive.
No,
Sorry,
but if you're
on the
gaining,
object, on the mass. We shouldn't confuse
but
the
if
two
you're
analogies.
gaining potential energy,
In electric potential,
yeah, or yeah, huh, yeah.
so the force that is, let's take this situation. So if you bring the Q closer, it's going to have higher electric potential over here. Then when you release it, so-called release it, the object will accelerate in this direction. The charge will accelerate in this direction. So the force that is being applied is going to be in this direction. The displacement is also in the same direction. So the work that will be done by this charge on this charge will be positive. The way I look at it, it seems to me like that, thinking about it logically. Tell me if it's not sitting well with you. Okay, so therefore now we can come to talk about electric potential. So a charged object placed anywhere in the universe, for that matter, will have an electric potential with reference to a particular other charge, correct? So you do have a gravitational pull that is acting on you from Jupiter or from the sun or from the moon, right? And then you can ask the question, is there any place in the universe where I will not feel that gravitational pull of the sun? Okay. And conceivably, if you look at the equation, there is no possibility, because the distance can keep increasing, the force will keep decreasing, but there will not come a time when the force becomes exactly equal to zero, unless the distance tends to infinity. Okay, so when the distance gets closer and closer to infinite, whatever that may mean, then the force is going to become closer and closer to zero. So in mathematics, just to go a few years ahead and look at the concept of calculus, we say that as r, the distance, tends to zero, as r tends to zero, then, sorry, not zero, I should say infinity, then the force that is experienced tends to zero. Does that make sense?
Yeah.
Okay, so forget about gravity now, come back to electric potential. The reason why so you may ask the question, okay, in comparison to this position has greater electric potential, but why does it have electric potential at this point also? What is that in comparison to? So we can't keep saying, okay, create an arbitrary position, from there it has lesser potential, but from some other position it has higher potential. To state it without any ambiguity, so to unambiguously state it, any charge at any position has an electric potential, and that electric potential is the amount of work that was done to bring it from infinity to that point. Okay, then you can say that anywhere you place the positive test charge q1 with reference to this charge, large charge q, it will have a potential. Where will it not have potential? It will not have potential only at an imaginary place which is infinitely away from this object. So that defines what your electric potential is. I hope this is clear. If there are any questions, please ask me now.